Understanding the fundamentals of Docker is essential if you want to avoid days of frustrating debugging, having application vulnerabilities, and also having unmanageable applications. Here at Avelx Academy, we believe in understanding the fundamentals of computer programming, infrastructure, and app deployment is essential to becoming a full-stack developer. Docker lets developers package an app and everything it needs, like code, settings, and libraries, into a single portable container, so it runs the same on every device. Think of it like putting your app in a sealed box that works identically on any computer, avoiding it just works on my computer problems. Instead, it can work on your whole team's PCs and scale very quickly across your back-end infrastructure, your servers, as well as your team. The first fundamental is very personal to me because if I understood this 20 years ago, I could have prevented my website at the time from completely crashing. Fundamentally, containerized apps can scale up and down and be replicated across infinite environments with ease. Think of a container as a virtual machine. Virtual machines run any compatible image, like Ubuntu or KDE Neon. Images are snapshots, like an install CD that can be replicated infinitely. Unlike virtual machines, containers don't need to allocate CPU storage or GPU. This will be handled by Docker automatically. Virtual machines also require the minimum storage requested by the image. However, Docker shares the image between containers, saving on storage. Containers mostly run Linux because it's free to distribute, unlike Windows and, of course, Mac. We can build our own custom Linux images to run in the containers. If I have a team of people manually configuring all those OSs with infinite configurations, it's like playing a game of Minesweeper. Configure once and run everywhere with ease with containers so that it's simple and easy to navigate and debug. Just like with any application, the most important aspect is communication. The World Wide Web is a network of computers networked by ISPs or internet service providers. Then you have your subnet or home network on the World Wide Web, which is your router and your subnet of devices you connect to your network. Your home subnetwork allocates each device in a unique IP. Each device has ports. Each port has a number from 1 to 65,534 and allows programs to navigate on available ports or incoming data. Your OS has a program listening on ports for incoming data of new updates that will come. Only one program can run per port, as anybody can tell you that running 2 React.js NPM projects on one port will result in an inevitable error. Docker creates a subnetwork hosted on your PC or server. It allocates IPs to each container and allows ports to be exposed to send data to your programs running inside the container. The Docker subnet can be exposed by the host port and map to the Docker container. This allows the host to communicate with Docker's subnet of containers. A container can expose multiple programs, but you should keep your containers as small as possible, mainly just running one program only. So you can see the physical network, like the World Wide Web and your home network or subnetwork can also have virtual networks inside of your computer, known as the Docker subnet. Let's go ahead and install Docker Desktop. Launch Docker Desktop and make sure the Docker service is running. When you install Docker, it also installs a Docker CLI tool accessible via your console. Docker has its own AI helper called Ask Gordon. Next, there is containers. This lets us see the currently running container environments. We also have images. The images are like the Linux Live CD images that can be installed to Docker containers as well. Images can be our custom images or ones downloaded from Docker Hub. Docker Hub is a place where you can store your images on the cloud and share with your server, team, or the world. Docker Hub is like the NPM for Docker. You can search for publicly available images and people have already made images. Volumes will also be used for persistent storage. It's like having an external hard drive for your containers. Build shows us the history of our custom built images. Docker has something called Hugging Face that actually is really exciting with AI and LLM technology, pre-built models that you can download from their repository. And we also have the ability to run that and then use MCPs. MCPs allow our LLMs and our machine learning models to be able to access apps outside of the model. So we have an LLM, then an MCP to access Gmail, and then it can check if my latest order has come through. So this is where we have something really special because the LLM cannot access Gmail directly, but when we use an MCP, it allows it to connect to external applications. Docker Scout is used to scan your images to show software vulnerabilities, make suggestions, and show you better alternatives for your software dependencies. It's just a really great helper in trying to discover not only security vulnerabilities, but make great suggestions that could help your container run better and more securely. Docker dashboard extensions add additional integration. A good extension is Open Web UI that'll provide a nice UI interface to interact with our LLM models. Super cool, right? I mean, it's AI. Now let's take a boilerplate React.js project and containerize it. First, we need to build my React.js project, which will produce the app files I need to containerize. Now we need to create a Docker file that will be the build instructions for our container image. First, we can look on Docker Hub for pre-built images that we can use. I'm going to choose the Node.js Alpine image. The Node.js image is basically Alpine Linux with Node.js installed. Using the from keyword in our Docker file, we can type the name of the image from Docker Hub. But now we want to customize this image. I need the HTTP server package from npm to be installed to serve my React.js project. Using the run command is like you opening the terminal on your virtual machine and running commands directly inside the container environment. Using the run, I can install through npm the HTTP server package. Next, working dir or work dir is used to set the working directory, and this will be the default entry point in the containers file system. The working directory command will create a directory if it's not found. So we're creating the app directory in the root of the container. Next, use copy to clone my React.js build files from the PC into the app directory inside the container. We need to expose port 3000 to the Docker subnet. The cmd command will trigger when starting the container. Let's run the HTTP server program and expose my React.js app and make it listen on port 3000. Our Docker file now has all the instructions to build our image, so let's go ahead and build it. Open the console and cd or change directory to where our Docker file is. Then run docker build -t for tag, and then give your image a tag name and a tag version after the colon. The tag version is in the format of major, minor, and update, a lot like npm packages. This will help you track any changes made to your images and understand any updates, whether they be major or minor. And it's very important you do keep track of this. Then add the build directory. I'm already in the correct place, so I just want to type the dot, and then Docker will look for the Docker file and build the Docker image. Once built, you'll see it in the Docker desktop. We can upload this image to Docker Hub with the tag name and version being very important to track your image. Now, this is just the image, like a CD with Linux on it. We need an environment to run it, a container. Type docker run and configure the ports. The first port is exposed on our host PC, and the second is the Docker subnet port, which in our case is 3000. Docker will find the correct image from the tag name, then all traffic from the host port 8080 will be mapped to the Docker subnets container, and that will be port 3000. You can now see our React.js app with the host 8080 mapping straight to port 3000 and delivering to our host PC the website, the React.js app. If you don't know this next fundamental skill, you'll find debugging extremely hard, as now we have a problem. I've made another iteration of my image and it has a bug. Now we can review the logs of the container and any console logs that came from your application in Docker Desktop. We should use the console though, however, as servers don't really use a GUI. Let's run docker ps that lists all the containers that are currently running. Next, we use docker log and then the container name to see the same log messages. Now let's log in to the container environment like a virtual machine and use console access to debug the container. Let's invoke docker execute or exec using the -it flag. I leaves the session open. T is for the tty sudo terminal, followed by the container name, and in my case it's going to be my React app. And finally, the shell environment we want to run, which is bin.sh. Think of this as adding a shell to our container so we can mess about with it, debug it. I can now install apps, the brand of Linux, which in this case for Node.js image, it's running Alpine. So as we're running Alpine Linux, I'm going to go ahead and install curl inside of that container environment using APK, which is for Alpine Linux. And then what I can do is check that indeed there is an application running on port 3000. Now, when I actually run this, I find out that in this container, there's nothing running on port 3000. Well, there's the issue. We've exposed this port on the Docker subnet, but it's not going to connect to anything. The end result is you're just going to get something that's not found. So what I do is I simply look into it and I find out that my HTTP server needs to change over to port 3000. I've misconfigured my Docker file and instead it's serving on port 4000. Well, that won't do for me, so I'm going to change it back to port 3000. I've found the bug, and then I can rebuild the image and retest it. Once we rebuild it, we'll find that this time my React.js application will work. This shows you the absolute benefit of being able to log into a container and able to run commands and find out if there is any issues. However, this next fundamental skill is very important when you need storage for your containerized app, and that's understanding how persistent data works. For example, we have a database container and we want to store user information. Let's pull the Postgres image from Docker Hub by typing docker pull Postgres. Now we'll run Postgres in a container and add a database. Log in to the container using the docker execute command. We're not going to go too much in detail about Postgres, but essentially, I'm switching to the Postgres pre-configured user, creating a new Avelx Academy database, and then creating a table to store usernames and passwords, which I will populate. If I stop and then start the container, you can see that when logging back in again, that the data is still there. That's because the container instance hasn't been destroyed. Now I'm going to stop the container. Then I'm going to completely remove the container and then use the docker run command to create a new instance of the container. I'll log back in with the docker execute command, and what I want to find is the database Avelx Academy, and you'll notice the database and user data has been completely gone. This is because by default containers have ephemeral or temporary data storage. But how do we make this data persistent even if we destroy the container? This is where volumes come in. Think of a volume as an external hard drive that can be plugged into many containers. But even if the containers are destroyed, the data on the volume will not be removed. Firstly, run docker volume create, then the volume name, which I'll call Avelx. You will now see this volume listed in the Docker desktop. Unlike normal volumes that plug into your PC and allocated as a separate drive, you can choose where to mount these volumes. So you can mount this volume as if it were a part of the file system of Linux, or the containers file system. Let's embed the Avelx volume at the directory var lib postgres, which is where the database files are stored. And of course, we need to do this configuration in the command. The docker run command with the -v or volume parameter, and I'm going to pass the volume name Avelx and where I want to mount the volume at, which is var lib postgres. This means I don't need to go out of my way to reconfigure Postgres to point to some volume. I can just embed the volume into the containers file structure. Cool, eh? Now we're going to log into the container and again add all the data to Postgres. So now, after I've added my Avelx database, I'm going to delete the instance and then rerun the same instance of Postgres again. You can now see when I log in, that data has been saved successfully. Docker also has cool ways of backing up your volumes and managing them as well. But there we have it. I pulled together a Docker cheat sheet which you can use as a Docker library as you develop your apps. You'll find a link below. Now you understand the fundamentals of Docker. The next level is understanding Docker Compose concepts, and here are the main concepts you need to understand. So take a look at some videos here.